Hello everyone, this is Kitish here. In this video, I'm going to go through the AQA Physics Paper 1 Higher Tier from 2023. Question number 5 is on the topic of atomic structure. Some isotopes emit nuclear radiation. Carbon-14 and carbon-12 are isotopes of carbon. Compare the structure of an atom of carbon-14 with the structure of carbon-12. Now, because they are both carbon, they should have the same number of protons. Now, carbon has 6 protons. So if you look in the periodic table, carbon will be 6 and 12. This is a general carbon atom that is found most commonly, but we have carbon-14 as well, which is C614. So they have the same number of protons. And what's different about them is the number of neutrons. This carbon has 6 neutrons, and 6 protons, and this has 8 neutrons and 6 protons, and they have the same number of electrons here. For this question, that wouldn't matter much. So the similarity, you can write it as similarity and difference separately. They have the same number of protons and they have the same number of electrons. The difference is the number of neutrons, or you could say different mass number, because the number of protons and the neutrons add up to the mass number. So we have to mention the electrons as well for the third mark here. So mention the number of protons, electrons, and the neutrons, because they're referring to the structure of the atom, not of the nucleus. So that's why generally they wouldn't bother about the number of electrons. Here they are talking about the structure of the atoms. Next question, 5.2. Carbon-14 is a radioactive isotope. Carbon-14 has a half-life of 5,700 years. What does a half-life of 5,700 years mean? Now, there's different ways of describing what half-life is. In terms of activity, it is the time it takes for the radioactivity or the activity of a sample to reduce by 50%. In terms of number of nuclei, you can describe this. Again, we are waiting for the number of unstable nuclei to decay by 50%. So here's a couple of different examples of half-life definitions. Any of this is actually going to give you a mark. The time it takes for the number of nuclei in a sample, radioactive sample, to half. So here we are talking about the number of nuclei. Or you could say the time it takes for the activity of the sample to half. Or you could say the time it takes for the radiation emitted simply rather than activity. Or you could say the time it takes for the count rate of a radioactive sample. And finally, we can talk in terms of the mass as well. The time it takes for the mass of carbon-14 in a sample to half, which is 5,700 years. Next part. Table 1 gives the half-life of some of the other radioactive isotopes. So here you have nitrogen-18, which is 0.62 seconds. Nitrogen-17 is 4.17 seconds. Fluorine is 64.37, and fluorine-18 is 6,584. So fluorine, it's actually going from the shortest half-life to the longest half-life here. A sample of fluorine-17 has an activity that is 1/4 of its original activity. Calculate the age of the sample of fluorine-17. Now, if it has 1/4 of its original value, so if we start off with 1, after 1 half-life, it should have half remaining. After another half-life, that half is going to half again, which means that's 1 quarter. So that's 2 half-lives. If it's gone through 2 half-lives, fluorine-17 has a half-life of 64.37. So multiply 64.37 multiplied by 2 half-lives. That should give me 128.74 seconds. 128.74 seconds. Next question. All of the isotopes in table 1 emit beta radiation. Explain which isotope would cause the biggest risk to a person's health based only on the half-life of each of the sample. Right? So based only on the half-life, the biggest risk is a radioactive sample that is decaying really fast. If it's decaying slowly, or if it has a much longer half-life, the activity is not as high as something that is decaying rapidly. So we are looking for the isotope which decays the shortest, which was the top one, nitrogen 18, which has a half-life of 0.62. So nitrogen 18 carries the highest risk. The reason being, it has the shortest half-life, which means its activity is greatest. So nitrogen 18, because it has the greatest activity, so greatest dose of radiation is absorbed per second by anyone who's exposed. Next part. People who work in the nuclear power industry need to be aware of irradiation and contamination. Describe the difference between irradiation and contamination. So irradiation, when you are exposed to, right? So for a short time, so like standing in the sunlight and then stepping back into the shade again, you've been exposed to the sunlight for a short time. Contamination, when you get the material on your body. So if it's stuck to your shoes or your clothing, or even if you inhale it, all of them are contamination when the material is physically on your body. So the difference, irradiation is the exposure of an object or person to radiation, while contamination is the unwanted presence of radioactive material or atoms on an object or person. Next part. Give one health risk to a person while working close to a source of nuclear radiation. If they are working close to a nuclear radiation, the one health risk is that nuclear radiation are ionizing, and because they are ionizing, they can cause mutations in our cells. Eventually, it can cause cancer, death if it's too much. So any of these is fine. Anyone from cancer, tumors, or DNA or genetic mutation or damages, or it can kill cells, or radiation poisoning, or you could say sickness, or you could say burns. 5.7. Workers in a nuclear power stations are monitored to check the radiation they emit. A worker stands 1 centimeter away from a nuclear radiation detector. The amount of radiation the worker emits is recorded. Explain why the worker needs to stand close to the radiation detector. Now, there's 3 different types of radiation that they could emit: alpha, beta, or gamma. Oops, it's not alpha. That's alpha. Alpha, beta, or gamma. Now, alpha has the shortest radiation. Not radiation. The distance it can actually travel, which is a couple of centimeters or less than that, and then gamma can be a couple of meters. So Explain why the worker needs to stand close. Well, if they don't stand close, they won't be able to detect the alpha. So, some radioactive material emit alpha radiation, which has a very short range in air. You need to mention alpha and that it has a very short range in air. Next part. Workers in the nuclear power industry are exposed to nuclear radiation. Pilots on aircraft are exposed to cosmic radiation from space. The daily dose caused by working in nuclear power station is 0.00050 MSV. Now, MSV stands for millisieverts. Sieverts is a way of measuring. SV stands for sieverts, which is a way of measuring radiation or a unit of measurement. Hourly dose from cosmic rays a pilot while flying is 0.003 millisieverts, which is slightly higher than the daily dose received by the nuclear power station worker. Calculate the number of days it takes for a nuclear power station worker to receive the same dose as a pilot flying 24 hours. Now, a pilot flying for an hour is receiving 0.003 millisieverts. So in 24 hours, if I multiply those two values, 0.0030 times 24, that gives me 0.072 millisieverts. That would be the daily dose of a pilot. Right? So calculate the number of days it takes for a nuclear power station worker to receive the same dose. So if I divide 0.072 divide that by the dose received by the nuclear power station worker, which is 0.00050, that would be, let's bring in the calculator for this just to make sure. So 0.072 divided by 0.0005, that's 144. That's a whole number, 144. That will be 144 days. That brings us to the end of question number 5. I will see you in question number 6.